Alright, welcome to episode 2 of Thermodynamics. Today's episode is going to be the second and final episode on chapter 1. A U2 manometer is just like a pressure measuring device using static fluids. You probably know pressure is equal to a force over an applied area. The classic example is if this is your foot and someone steps on it with their shoe, which I guess this is their shoe, it's not so bad because this is the applied area. On the other hand, if someone steps on your shoe with a high heel, it's not so good because I don't know what high heels look like, but you have this applied area right here. It's going to hurt a lot more. It looks more like a chicken than a high heel. So there are 3 different types of pressure that we usually talk about in, well, not really in thermo, honestly. After chapter 1, it kind of just goes out the window. You're going to hear more about it in fluid mechanics. But absolute pressure is the true pressure. It's gauge pressure plus atmospheric pressure. So what is atmospheric pressure? It's just the air around you. It's like roughly 14.7 psi. And gauge pressure, it's just measuring pressure relative to the atmosphere. And I came up with this analogy. It's not perfect, but it's kind of like weightlifting. You go to the gym and you're like, yeah, today I hit a new PR. I did 2 plates. And so the 2 plates, it is counting the plates themselves, but also the bar. But we don't say, I did 2 plates and the bar. We just say we did the 2 plates. Gauge pressure corresponds to the plates. You lifted 2 plates. But we all intuitively know there's the bar, the atmospheric. And if you consider the system overall, the bar and the plates, you have absolute. So absolute is kind of like the true weight. Gauge pressure is kind of like the plates that you put on the bar, and then the bar is like the base weight. So we kind of talked about gauge pressure, and we're just like, it's relative to atmosphere. But the way we usually measure it is through 3 different components. So it's dependent on rho, which is the density, g, which is the acceleration due to gravity, and h, which is like the elevation, or usually it's elevation change. You might see it as z, you might see it as L, same thing. And so what this kind of means is you can have a pressure gauge, like a manometer, that goes like this, it goes through all these wonky shapes, and it ends here, and it's a really bad drawing. This point right here, assuming we just do a straight line right here, these 2 pressures are the same. It doesn't matter that it goes down here, it doesn't matter that it goes right here. So long as the elevation matches and the fluid is uninterrupted, it's going to be the same. Building on that, if we said there was a fluid change right here, so this side is now fluid A and this side is fluid B, we can't say these guys are the same because there's some different change in density, and that's going to change it up. So in this problem, we're asked to find the gauge pressure of this tank right here. And we have 3 fluids involved, and not including the air right here. We're kind of just going to neglect elevation changes and say that pressure here is equal to the pressure at the gauge. And that's generally how a lot of these manometer problems work. Usually it's like elevation change is negligible, or density is just like so small that it's like not really relevant. Basically, the best way to approach these problems is to just kind of look at it and go point to point and get to the answer. We're going to call this point A, call this point B, point C, and point D. So at point A, we say it's open to the atmosphere. Pressure at A is just equal to the atmospheric pressure. So what that means is pressure at A is equal to the atmospheric pressure. So if we're talking gauge pressure, we need to go back to that definition of absolute equals gauge plus atmospheric. And so we know that we're measuring gauge based off of the atmospheric. So what that means is if we're at atmospheric, we can just say pressure at A is equal to 0. If we were to include atmospheric, it wouldn't be a hard process. It's just like add the atmospheric pressure at the very end. We can even do that in a second. Let's go A to B. And this is where we'll start using that rho GH equation. So pressure at B is going to be pressure at A plus the density of oil times the acceleration due to gravity times that elevation change from point A to point B of 3 meters. This should make sense because as you get lower, the pressure is going to get higher. So now we're going to go from point B to C. You don't even need the mercury in this problem. You don't need the density because you can just say pressure at C is equal to pressure at B. So C and B are at the same elevation, and you have the same uninterrupted fluid between them. Now we just got to do C to D. And now we're going to say pressure at D is equal to pressure at C minus the density of water times the acceleration due to gravity times the elevation change, which was 2 meters, I think? And so now we just got to kind of plug everything in. Pressure at D is equal to pressure at C, which is equal to pressure at B, which is equal to pressure at A, which we said is just atmospheric, so it's just 0, plus the density of oil times the acceleration due to gravity times that elevation change of 3, and then this is all PC, which is equal to PV. And then we have this third term of rho of water, acceleration due to gravity, and then the 2 meters between C and D. We're just going to plug in our numbers. We're just going to do the units for one term. The density of oil we said is just roughly 950 kilograms per cubic meters times the acceleration due to gravity. We're just going to say it's 10 meters per second squared because it's easier. And it's 3 meter elevation change. So now, let's look at our units. We have a kg, we have meters per second squared. That we know is a Newton, and then the meter divided by meter cubed would give us meter squared in the denominator. What you're left with is newtons per meter squared, which is in fact a unit of pressure, and this equals 1 Pascal. And then we just have density of water, which is 1,000, and I'm not going to do the units, it's just 1,000 kilograms per cubic meter, 10 meters per second squared, and 2 meters. And that should give us an answer of 8,500 newtons per meter squared, or Pascal, or we can say it's 8.5 kilopascal. And this is the gauge pressure. Finally, we're going to go back to the equation of absolute pressure equals atmospheric pressure plus gauge pressure. And I think it's 101 kPa. And in the end, you would get that absolute pressure is equal to 109.5 kilopascals. And that's the absolute pressure at point D. So this is going to cover the end of manometers and the end of chapter 1. Manometers really aren't too bad. They just look hard and confusing, but they're really simple once you kind of see how they work and do one or two. I hope this helped. If there are any questions, just let me know. And thanks for watching.